Just a couple more minutes. Before we start, guys, I just want to ask if anybody saw a phone. Let us know, because someone in the conference lost their phone. Thank you. Okay, Quang, yeah, you can start.
All right. Okay. So people can hear me? Okay. I hope that's
Yes.
good. All right. So yeah. Thanks for this opportunity to have basically all of us who are working on ArkLib to talk about our work today. And so I will round it up by talking about how the foundations of ArkLib are changing. And this is very much ongoing work. I will try to keep this talk concise so that we have plenty of time for questions. Okay. And of course, this is not possible without all the wonderful contributors to ArkLib, which I list here, although I'm sure that I'm missing many others. So let me go ahead. Yeah, so the ArkLib, what I think it's worth to maybe take a step back and think about the context of why something like ArkLib exists. And the reality is the snarks, as we all know, they're now being used in production. And that means that any bugs that occur at any layer of the stack can have devastating consequences. It can lead to soundness breaks, which leads to loss of money, and so on. So the only way that we know how to reliably eliminate bugs is to formally verify these snarks. Now, on one hand, on the arithmetization or the circuits end, we have many verification frameworks already. And I list some of them here, and some of them I might have not been listed. And so all of that is on the circuit level. What about the protocols themselves? How do we formally verify them? And once you look into the protocols, it turns out that, of course, they have many non-trivial mathematical contents, especially in coding theory. And so as we formally verify these, I think we're also contributing an independent contribution, not just to the Snark community, but also to the broader crypto, CS, or mathematical community. And that means that we should be formalizing these beautiful results on correlated agreements, proximity gaps, and so on. And finally, a bit of a historical note is that ArkLib, as of right now, has been in development for basically 2 years. I started this as basically a side project on my own, and it's gradually grew to be part of the verified ZK EVM effort since 2025. And just a personal anecdote is that when I first started knowing nothing about Lean, I was wondering, like, how hard could this be? You see all these protocols that people write on papers. You see all these proofs that go along with it. And well, it's probably not too difficult to encode them into Lean, right? And well, turns out, as with everything, it's a lot harder than one would expect once we really get into it and try to build a good framework that can capture basically every protocol that we know of. So let me also go to what ArkLib is right now, and or at least the goals of ArkLib that we hope to provide now and in the future. And I think we would like ArkLib to be basically a place where any Snark protocol can be specified in a modular way, achieving specifications that are executable. So you can actually run it. You can it can be tested against production implementations. And right now, our focus is on these generic polynomial IOPs, and also on the hash-based polynomial commitment schemes, although these focus might shift in the future as well. The second goal is that we can't just specify these protocols, we have to prove their security. And if we are modularly constructing these protocols, we should also have composable security proofs for these protocols. So it's sort of like going the same way as we build these protocols, that's how the security proofs needs to go as well. The third thing is that we can't just have individual components. We must find ways to glue them together and to compile them into actual snarks that can run in an end-to-end manner. And that means that we need to formalize these fairly complex compilation steps, which includes the interactive BCS transform, where you turn an IOP basically into an interactive protocol. And then you turn that into a non-interactive protocol with Fiat-Shamir. So I'm sure everyone in the audience know these transforms, and it is part of ArkLib's goal to formalize these once and for all, so that you only need to specify the protocol at the IOP level, and then all the rest go through. And that means, in particular, you would eliminate all kinds of bugs due to the application of Fiat-Shamir, for instance, because you start from something that is already interactive and you fully specify them, and this compilation step to Snark with Fiat-Shamir is a completely generic transform that we prove secure once and for all. And well, finally, we have something in Lean that is end-to-end, only in Lean end-to-end formally verified, but the final part is you have to connect it to implementations of production code bases. And I know this is ongoing work. People are using hacks, I think, among other tools, to extract the Rust code in popular libraries like Plonky Free into Lean, and then formally verify that it matches the specifications in ArkLib. So these are all the goals. These are, I would say, fairly ambitious goals. And it's worth noting what is our progress in achieving these. And in some sense, I would say our progress is non-trivial, but we still have a lot to go. The core of what ArkLib provides today is that we give a framework for specifying interactive oracle reductions. And so a quick refresher on what IORs are, you can see on the right here. You basically have two parties, prover, verifier. They start with some statement and some witness. The statements here consist of two parts, one that is public to the verifier, and the other one is only available to verifier as oracles, with some specified interface going along with each oracle. Now, the two parties will exchange messages. Verifiers' messages are random. Provers' messages are either oracles as well or some public data. And these kinds of oracles are basically, you have vector queries, polynomial queries, and so on. Okay. So that's the general interaction. And at the end, prover and verifier is going to output some new statements and witness. And this reduction viewpoint is basically how we can compose these smaller reductions together to form bigger reductions, and that leads to whole protocols. So it means that now we have specifications of various protocols in ArkLib. Of course, we also need to define these generic transform. So we have defined the Fiat-Shamir transform, and especially the variance that is used in practice most often using a duplex sponge. And we have stated the security properties for them. And finally, we have a large and well contributed coding theory sort of sub-library within ArkLib. So we have all the important definitions written down. We have proved, we have made very good progress improving some of these, as you may have learned about in Katie's talk and others' talk as well. And yeah, it becomes an important independent contribution of ArkLib in its own right. So this is what we have. What I would like to point out next is what we don't have. And these become, or these are caused by some of the choices when you go into the deepest level of how we formalize IORs in ArkLib. So let me go just straight to these, I would say, pain points. The first pain point is that if you look at ArkLib today, the structure of a protocol is fairly dependent. So a protocol depends on the number of rounds n, and then within each round, or within each message exchange, you have who is speaking and the type of that message. So far, fairly standard. This is how you would define, say, like a 3-round Sigma protocol. So that's okay. The problem is that you have this dependence on the number of rounds here. And Lean is a fairly fussy theorem prover, as with many others. What it says is that so this is something that's a little bit technical to Lean, but the upshot is that you have to be casting, you don't have equalities for free. Some equalities come for free, others do not. And the ones that do not, you need to provide a non-trivial proof for them. And when you provide such a non-trivial proof, as you can see here, 0 plus n is not definitionally equal to n. It means that you have to be inserting a lot of cast into these protocols. And this is just the cast at the structural level. Imagine the cast that's going on when you specify the provers algorithms, for instance, and then you have to compose these provers. Here is what this composition actually looks like in ArkLib today. What you should see is that really the main contents are these green boxes that I put in here. But in order to get to these green boxes, you need to do a bunch of simplifications and a bunch of casting. And this has real consequences. The consequences are that it's nearly impossible to prove any theorems about these definitions. So yeah, you can see that here are other snippets in ArkLib. It turns out we are not able to prove these yet. Perhaps if we try really hard, we can. But this sort of points to a need for better definitions overall so that we don't run into these issues. And so, yeah, even something like a general sum check protocol do not have an end-to-end proven security in ArkLib today. Because we can specify everything, we can prove the security of, say, a single round of sum check, but we don't have these generic theorems to conclude that the security of the whole protocol is complete and sound. Okay. So that's the first problems with ArkLib today. The second problem is that ArkLib doesn't quite support some kind of protocols that start arising in practice. And the problem is, here I give you this definition. It has a fixed number of rounds n, and within each round you have some predetermined direction and the type of the message. This suffices for most protocols, so that is great, but there are some protocols where this just doesn't apply. For instance, you can think of, say, like a ZKVM, where as part of the proof, you send some metadata, say the number of rounds, how you arrange the polynomials, and all kinds of stuff. And then the rest of the protocols, for instance, the number of sum check rounds would depend on these parameters. A second line of work shows that, well, if you say if you work for snarks over the integers, what you often do is that the verifier would then send a random prime, and then the rest of the protocol works over that random prime. And so it means that in later messages and later structure of the protocol depends on the values of earlier messages between either the prover or the verifier. So, and currently, we have no way to represent these protocols in ArkLib. The second problem within these larger pain points is that it's perhaps a technical point on how we actually define what it means for this Y2, this output oracle statement, or output implicit instance. How is it actually defined in terms of everything that we've seen so far? Okay, so note here that the verifier doesn't see technically what these Y2 are. That's the whole point of them being oracles. And one way you could say, and this applies in most cases, is that this Y2 is simply a subset of all the oracles that verifier sees so far. This works for many protocols, but not for all. If you want to take a particular example, you can think of the batch fry protocol or batch PCS for any kind of PCS, like hash-based PCS. What you have is that the prover will have a bunch of polynomial oracles, and they want to have a batching step where it would send another polynomials that is supposed to be a linear combinations of the ones so far. So that doesn't quite fit with the subsets kind of semantics. And just in general, if you think about what does it mean for an oracle family to be defined in terms of other oracles, that gets you into some interesting territory. And yeah, the general approach here is that you say you have access to Y2, it can be simulated by using the public information and using the oracle access to all the prior oracles. And that should be the general way in which this is defined. Okay. The third problem is basically a usability problem. What we have right now in ArkLib, for instance, when you try to when you formalize the subject protocol, or any protocol for that matter, is that you have to define a bunch of definitions. Of course, you need to specify it. And what the specification looks like is that first, you need to specify the protocol structure, and then you specify how the prover works, how the verifier works, and then you have the reduction, which is just the combination of these two. And when you try to build further reductions, what you do is you do one of these composition operators that we provide, for instance, sequential compositions. So sumcheck is a particularly nice example because you just sequentially compose all the individual rounds. But well, if you look at this, this is okay. I basically didn't expand out all the definitions of the prover and verifier and so on. But if I do, then it easily gets you to a few hundred lines of code. Some of these are inevitable, but if you think about how these protocols are defined on paper, it's a lot more concise. And importantly, what's concise about it is that you can see the full protocol structure and how the prover and verifier interacts within a single definition, like a figure. Whereas here, it is split between prover, verifier, reduction, protocol structure, and so on. And this makes it harder to read for the reader to keep in mind all these different definitions. You have to go back and forth. And of course, this would increase the risk of misformalizations. And it is actually something that misformalizations do occur in ArkLib, and we have been very vigilant in addressing them. And this is one of the things that can increase that risk, and we should be fixing it. Okay, so those are, I would say, the main pain points that you would see in ArkLib today, and I would really like to address. So let's try to evolve the foundations of ArkLib to a place where these pain points go away, and potentially other pain points that I didn't mention yet. So in this quest, well, how do we know if the new definition that we choose are the right ones to build upon? So the definition of right here is certainly subjective, but we can sort of asymptote it by looking around, say, not just in the cryptographic community, but you look at programming languages, category theory, game theory, etc., anywhere where people have been dealing with the problems of, say, well, how do you formalize things in theorem prover? How do you formalize an interactive protocols? How do you formalize Oracle access and so on? Then that gives you pretty close to what I think would be the consensus of how these protocols should be defined. So I will just mention two things here. The first thing is that it turns out there's this kind of object called polynomial functors and free monads over them that provide a really good base for specifying both Oracle access and for interactions. And really, they are two sides of the same coin, as you'll see. The second way, the second innovation in PL that we bring or are hoping to bring is that of choreographies. And what that means is precisely the concept that you could specify an interactive protocol in a concise manner using a single definitions that look like the figures that you would see in Stark papers. You have every definition sort of put together in one place so that you can easily see the structure of the protocol and how it is defined. So this is a very active rewrite of the library, and I don't have the full ready version yet. There are some open questions that I think is remaining, especially how these general formulations interact with the particular formulations or of particular compilation steps, say Fiat Shamir and BCS, and so on. So I think we need to work these things out and make sure that they are the way that we think they should be before we could really supplant the foundations of ArkLib. So for the rest of the talk, I'm going to go briefly into these two things, these two techniques, and sort of preview what the improvements are. Okay, so polynomial functors, what are they? They are really, you can think of them in many ways. The way I like to think about them is that it's just describing a dependent types of protocols. So A polynomial functor itself just consists of two things. One is the type of, say, the head, and the other thing is the type of the family for each value of the head. So here you can see the dependent types is baked into the definitions. This b here is a function that is dependent on the particular values of something of type A. To make it more concrete, you can have the free monad over this polynomial functor. And what that means is you take this structure provided by the polynomial functor, and then you do a sort of free construction or some kind of recursive definition on them. So this, what you should think of is you are describing an interaction tree. At the leaf, you have you can return some values, and more importantly, at each branch of the tree, you can have it can be decorated with a value of the head type, and then you specify what would happen with once you receive sort of the corresponding value of the child family, the child type corresponding to this head value. So you should really think of it as a branching interaction tree where the branching can be determined by the structure of this polynomial functor. This is in fact the viewpoint that we took for this VCVIO library that you may have seen in Devin's talk, which is that this is really like an oracle computations. You specify this is basically the dependent oracle type, and then this is you make an oracle query, and then you continue with the response. For ArkLib, you can reinterpret this as the base for the structure of a interactive oracle reductions. So to be concrete here, I give you sort of an unrolled definitions of how an IOR should look like, at least protocol-wise. You would be instantiating this with a particular polynomial functor, and what it looks like is that it can either be done, or the prover sends a message, and then the rest of the protocol may depend on that message. If the prover sends an oracle, then it needs to come with an interface for that oracle, and then the rest cannot branch on that oracle value because the verifier cannot see them. And finally, for the verifier, it can send a challenge, and then the rest of the protocol may depend on that challenge. So this solves the representation issues that I alluded to earlier on how protocols are dependent nowadays, and this cleanly solves that issue. You just encode that dependency directly into the definition. What this also provides us is that now the prover and verifier can be defined inductively based on just pattern matching on these various constructors. So what this means is that, this definition allows you to have, let's say the prover has some side effects, which is encoded by this M. For those in the audience who know, these are just an arbitrary monad. And the point is, the prover is now just a type. It is not a structure with many different fields. We do not need to provide sort of an implicit state for the prover. We do not need to manage it. We just say, here is the behavior of the prover at the input-output level, at the interaction level. We don't care about its internal. All we care about is that when the prover sends a message, it must send a message, and then it continues with the rest of the protocol. If the prover is expecting to receive a challenge, then it would need to provide output a function that can answer any challenge that it receives. So this becomes quite an elegant type definitions, and it gives you real advantages. On the verifier side, I should note also that it's a little bit more complicated than this, because you also have all these oracles going around. So technically, what you need to have is that this monad here may grow after each round to accommodate for the new oracles that the verifier have received. But in any case, the important point here is that when you define everything in pattern matching manner in this way, the sequential compositions that you would write, the definitions of them, they require no casting. They just require pattern matching on the protocol specifications. And the same thing happens for the security proofs as well. You just do the pattern matching, and that gives you a nice decomposition of the protocols. Okay, so that's actually led to quite far. At least what I can credibly claim is that in the branch that I'm developing this, I have proved an end-to-end round-by-round soundness of sum check in a generic manner. Of course, there's some debate here on what is the truly generic notions, and I'm happy to talk about them after this if anyone is interested. But basically, here are the headlines. The second thing that we try to solve is with, well, readable specifications, using this idea of choreographies in PL literature. And the idea is that here you have some protocols you define in this compact figure. Here I take a very simple example of Schnorr. You define the protocol in this way, and intuitively you see this and you know what each side is doing. You can also make this precise via a concept called endpoint projections. It just means that you have this unified definitions. It automatically gives you projections to a full description of the prover and of the verifier. Okay, and we can actually do this in Lean. So with the help of some sort of Lean meta-programming syntax and macros, we can write something that is fairly, what I would say it's very readable. So the point here is that the flow of the prover and verifier, it's all in one definition. And you can see in each round what each party sends. Here you see the structure of protocol baked into this. You can see what the prover is doing, what the verifier is doing, and you see what happens at the end of the protocol. So yeah, this is how you would, I hope that we could move to a place where we have a very succinct definitions or specifications of protocols in ArkLib without losing on any kind of generality. And of course, this notation needs to expand further to account for, say, Oracle access, Oracle queries in the IOR setting, and so on. This is just interactive protocol with no oracles. So that's another axis that I'm trying to push on, which is to get choreographies working well for these Oracle protocols. Okay, so let me summarize here. Well, as said at the beginning of the talk, we would really like ArkLib to have formal specifications and security proofs for all Snark protocols, especially those that are deployed in productions. And we are making really good progress towards that. We have many active contributors. We are heavily benefiting from the progress in AIs that can now write Lean extremely well. So even if you don't know Lean at a sort of an expert level, it is really easy for you to get started on writing Lean with the help of LLMs. And to support all of this growth, we need to be rethinking and rewriting the foundations of ArkLib in the right manner. What that means is that we need to make sure our definitions are the right one. And what the right one means is that this must be something that is sort of independently gotten to by people in other communities who have thought long and hard about similar problems. And what that would enable us is that we can finally have end-to-end security proofs, and we have specs that are readable to a regular cryptographer, not someone who needs to know the intricacies of Lean. So this is ArkLib. We always welcome new contributors, and we welcome existing contributors as well, of course. And yeah, you should check out the library, and thank you for listening.
And questions, please raise your hands, otherwise we won't hear you.
Testing. Can you hear me, Quang?
Yes.
On the Schnorr diagram that you wrote, I think it's 2 slides back.
Yep.
Yeah, so when the prover samples a random number, what is the right-hand side doing? Like the Schnorr, that part there. What is this?
Yeah, it's just like syntax sugar for random sampling. So what this means is that you would choose R independently at random from the whole finite field.
Oh, so when you said that there's no oracle access here, what did you mean by that?
Oh, right. So the prover here sends an actual message, like it sends this R times G, or like G to the R, instead of sending an oracle to G to the R, for instance.
Okay, thanks.
So the oracle part is like, yeah.
More questions? I guess that's it. Thank you very much. No more questions. If you have anything else to add, you're welcomed.
Thank you.
Thank you very much in this case. Quang, it was a pleasure to hearing you. Thank you for sharing your knowledge.
Does this work? Yeah. All right.